Hey, how's it going in the studio? I'm going to be talking about direct energy deposition, DED. Direct energy deposition, DED, is additive manufacturing, AM, or 3D printing technology used to create complex metal parts and components. It is also known as laser metal deposition, LMD, laser cladding, or laser metal additive manufacturing, CLAM. That is versatile and precise manufacturing process that involves the following key elements. Material, feedstock, that yeast, DID, yeast, a feedstock material in the form of powder or wire. This material is typically a metal alloy. The feedstock is direct towards the build area. Energy source. An energy source, often a high power laser or electron beam, is used to melt the feedstock material. The energy source is precisely controlled and directed to the desired location. 3D printing head. The 3D printing head combines the feedstock material with the energy source to create molten pool. It can move in multiple axes to deposit material layer by layer following a predefined 3D digital model. Build platform. The build platform supports the grounding part and can be adjusted vertically as the part is built layer by layer. Overall, just to summarize this process, at least the way how I'm thinking, depending on the setting, it might be required fast-paced performance. So if you were to think about the best process to how you can manufacture something at the speed and how you can do it, I'm always using an example of perhaps printers, and when you have to print, I don't know if that works, but that's at least how I'm thinking about it. And when you have to print labels very fast, those labels can be printed overall process, and once it's be printed, only would need to stamp the label to the package, or you would, in this particular case, you're using already piece of metal and you heating the metal, and then you're just stamping that metal already to apply to the surface where that surface would be required. So that's one way to think about it. Other way would be perhaps manufacturing. So I don't know if this analogy works very well, but instead of having those labels already ready, you could work of how you can integrate that material into the system other than this particular way. I can't summarize this example, but that's how it works. Otherwise, you wouldn't necessarily catch up with speed. There are different ways where you could get that material from. This particular instance, they having pre-rolled material, which goes into a system. They would heat that material, and they used for that system to pump that material. But then we think about what's the best and perhaps fastest way of getting that material from and using that material. You need to take that material from somewhere and then heating that material and then add to, instead of removing material off, you adding material to. So I guess I just like to summarize that you need to add, and once you add, you need to take it from somewhere, and how you can self reinvent the process, and how you can think about what kind of problem you actually have and what would be a best solution to solve that particular problem within industry, and the way how a lot of things, especially in engineering, when you look at the history, you can see how all the industry evolved over time, and there were a lot of smart people who were keep coming up with different ways. Would that be from agriculture, bringing something into engineering, as well as from engineering things bringing something to agriculture? from different sectors might come up with a better way of actually manufacturing this particular instance, feeding up raw material, heating up, and using that for surface layers. DED offers several advantages. Complex geometrics. DED can create parts with intricate and complex geometrics, making it suitable for aerospace, automotive, and other industries where lightweight and high performance components are required. Material variety. It can work with a wide range of materials, including various metals and metal alloys, which makes it versatile for different applications. Repair and cladding. DED can be used for repairing worn out damaged parts. Cladding by adding material to affected area. This is particularly valuable in industries like oil and gas, where critical components can be refurbished rather than replaced. Low waste, because it is an additive process. DED generates minimal waste compared to traditional subtractive manufacturing methods. Rapid prototyping. DED is also used for rapid prototyping, allowing engineers to quickly iterate and test designs. However, there are some limitations and challenges associated with DED surface finish. DED parts may require post-processing to achieve the desired surface finish, as they can be rough due to the layer-by-layer deposition. Heat management. Managing the heat generated during the process is crucial to prevent distortion and stress in the parts being built. Powder management. Handling and recycling excess powder can be challenging and costly. For those of you up there who would like to learn more, I have published a book. In this particular book, I'm sharing a lot of information with regards to fitness and what would be needed for you to expand your knowledge when you looking to improve your physical, would that be increasing activity level, your health, appearance, self-esteem, million things that everyone could always work on, I guess, depending. Overall, then thinking about your hardware that you're constantly moving around with, there can be a better way of perhaps understanding different sides of fitness, with the perhaps rest, training, and food, or perhaps your overall goals when going to the gym and what those goals are. And I'm sharing a lot of information in this book. I highly recommend if anyone to read it. You can find this book in the description below, as well as top retailers has it. Direct energy deposition is a valuable technology that complements other additive manufacturing processes. Some of those processes we're going to be looking at in the different videos. Overall, this particular process has ability to build large, complex parts and repair critical components, has made it an important tool in industries where precision, durability, and customization are essential. Let's take a look at some of the examples and where direct energy deposition can be used. In aerospace, building complex lightweight aircraft components such as turbine blades and structural parts, repairing damaged turbine blades or other high value components to extend their operation life. Automotive, prototyping and producing custom exhaust systems, suspension components, or other vehicle parts with unique geometrical sizes, repairing damaged engine components or transmission parts. Oil and gas, cladding drill bits with wear-resistant materials to expand their lifespan, repairing valves, pumps, and other critical equipment used in drilling and extraction processes. Tooling and die manufacturing, creating complex injection molding or die casting molds. repairing damaged or worn sections of molds to avoid complex replacements, medical, producing patient-specific orthopedic implants like hip or knee replacements. There's a lot of opportunities in that space, but there's where a lot of value within the current system. I have met a lot of people doing a lot of work within the medical space, creating custom dental prosthetics just based on how accurate all the parts need to be. Marine manufacturing, complex marine propellers, repairing damaged ship parts such as propellers, shafts, or rudders. Either way, I hope that covers everything. Let me know in the description if I have forgot anything or if there's anything I can add to it. Thanks for watching. I'll see you in the next one.